Boolean expressions, and we have already talked about Karnaugh map techniques previously, but let me just quickly remind you of what that is. So basically, the Karnaugh map is a graphical technique which helps us to simplify Boolean expressions. And what you really do is that you take the variables you have and assign cells to them. So here we are talking about 4 variable functions. So these are there are 4 Boolean variables A, B, C, and D here, each of which can take either the value zeros or ones. So we have 16 possible combinations. So we have a 16 cell Karnaugh map which is arranged in a 4 by 4 square. So this is for 4 variables. With 3 variables, for example, if we had a 3 variable scenario, A, B, C, that would have been 8 possible inputs, and that's usually portrayed as a 4 by 2 map. By the way, it's usually called the Karnaugh square, even when it's not a square. So the 4 by 2 rectangle is also often called a Karnaugh square. Okay. So the basic idea is these are the columns which have been given entirely to A, which means for every one of the cells here, A has a value 1. Every one of the cells outside these 2 columns, A has a value 0. Similarly, of course, that means that these 2 columns, this one and this one, basically make up A bar, the complement of A. Similarly, you have B, which has been given these 2 columns. So if you look at this specific column, this is where A and B are both high. This one is where A is low but B is high. So if you continue that way, this one, these 2 rather, this one and this one, are where A is, well, if you look at these 2, A does not feature into this because it spans both A and A bar. It falls both inside A's territory and outside it. But this is definitely inside B, in D, in C. So this will be B, C, D. So just to illustrate what this will look like, let me just go on and talk about slightly more complicated scenarios like this one. So this is not really complicated. All I'm saying is if you had A alone, A would have these columns full of ones, the rest full of zeros. So you would have an octet of ones, 8 contiguous ones. So here A bar, again the same thing, 8 continuous pieces of ones arranged in a rectangle like this. So this is the kind of structure that you should look for in a Karnaugh map. And the whole idea of the Karnaugh map is it sort of graphically allows you to take a look at the picture and decide, okay, I've got these structures, and this helps me simplify the full calculation. So 8 ones arranged like this will be A, 8 ones here will be A bar. Well, 8 ones here will be B. The B bar is slightly trickier in the sense that it will also have 8 ones, but it will have 8 ones like this, right? Outside B's columns. All the 2 columns outside B's purview, they will all be 1. And of course, those in B's column will be 0. So this is what you will have. Now, this does not look like 8 continuous ones in a rectangle unless you think of this as being wrapped around. So there's a topological issue here for those of you who are math fans. This is really a square or a rectangle, but with opposite edges identified. So if you think of, well, basically wrapping this around like, so that this becomes a cylinder, these 4 ones and these 4 ones are really next to each other. So that's the only tricky part. You have to sort of keep on visualizing the thing so that the 2 edges are identified, not only the vertical edges here, but also the horizontal edges, these 2. So it's not just a cylinder. It's really like a torus. If you think about it a bit, it's a cylinder which you then bend around so that the 2 ends come together, like a bicycle tube, for example, or a donut. Depends on which one is more familiar to you. So just to continue with the examples, this is, well, this is D because you can, okay, how do you quickly identify? There are 8 in a rectangle, so it must belong to one variable. And which variable is that? All of these are in D, none of them are outside D, so this has to be D. You can, of course, go by elimination. That is, it's not A because partly it's in A, partly out of it. Not C because partly in C, partly out of it. Not B because of the same reason, so D. This one is a rectangle with 4 elements. That's CD because they are both, they're in all C and D. These are just examples which I'm trying to show you so that you can get the various kind of structures you will get. You can get 8 things in a rectangle, 4 in a rectangle, or 4 in a square like this. But they have to be continuous ones, taking into account the fact that the 2 edges are identified. So these go together, they're in A, they're in C, and in fact, it's easy to remember this, that if you have 4 variable scenario, then single letters dominate 8 columns, 8 cells. 2 letters, whether they're A or A bar or C bar, B bar, doesn't matter, but 2 letters dominate 4 cells. 3 letters give you 2 cells. For example, these two together, these two individually would be 1 element each. So frankly, this one, if you really looked at it, what is this? This is in A. So you will look at this as A. If you just looked at this alone, it would look like A. Outside B, so B bar. Outside C, so C bar. Outside D, so D bar. Right, that's what it is going to be. What about this one? This is outside A bar. Outside B, B bar. Outside C, C bar. Outside D, D bar. So what is this really? This function that you see here is high when either this is high or this is high. Okay? So when you take them together, you get this or this. And if you remember your Boolean algebra, this really is A plus A bar into B bar, C bar, D bar. Well, into is wrong, it's and. A or A bar and B bar, C bar, D bar. A or A bar is 1 or true. And 1 and B bar, C bar, D bar is B bar, C bar, D bar. That's the algebraic way of figuring out that this is B bar, C bar, D bar. The Karnaugh map way is just I see that these two together form a rectangle of 2. So either look for 8 or 4 or 2. Of course, you could look for 16, but 16 would mean every one of the cells is 1. That's the trivially true statement or trivially true function. Here you have these two together, but remember these two are really together. That's one thing you have to, that's the only tricky part here. You have to think of this as wrapped around so that they make a full, they essentially are 2 ones sitting right next to each other. So here, for example, there are 4 corners of ones. Each one of them will be taken to be together because remember, not only do these 2 sides wrap around, these 2 sides also wrap around. And if you look at them together, you will. The easiest way to figure them out is all 4 are outside B, so they are B bar. All 4 are outside D, so it's D bar. So these 4 together make B bar, D bar. So any questions so far? Or is this okay? No questions. So let's move on to the slightly more complicated. No, this is not really complicated. This is where I'm giving you an example of how to use the Karnaugh map technique to understand the simplification business. So you have a function for which you have these as 1. So you write down the Karnaugh map first, identify which cells have 1s, which have 0s. I'm going to tell you a quick way of doing that after I finish with this example. But suppose you have the Karnaugh map already given to you. How would you simplify the Karnaugh map? So your idea would be try to put, the basic idea is larger the number of things that go together. Go together means you can have 1 cell on its own, you can have 2, you can have 4, you can have 8, you can have of course 16. So if you can put larger numbers together, then they are simpler. They have smaller number of variables involved. So here I can easily see, let me just try drawing this for you. So I can easily see one structure here. These are 4 together, right? And so that's one quad that I have actually identified. Now, in addition, what about this one? Do I take this alone? So can anybody tell me, do I take this alone? Well, I can't see anything else next to it, right? Somebody, can you please tell me whether I should take this alone as a entry like this? Or is it not making any sense? Any ideas? Should this go like this? By the way, if you take a look at this, what does it stand for? This is A in A, partly in B, partly out of B, so no B involved. In C, so this is really AC. You don't even have to look at D. I know 4 cells together means 2 letters, so it's AC. This one, on the other hand, is a single cell. If you took this, it would have to have the version. It's in A, in B, outside C, in D. So that's what this expression will be like. So if you took this cell alone, it would be that. You could take this cell alone, then you could take, well, what else? You could take this dyad, you could take this cell. You could do this. This is correct. However, this is not what the Karnaugh map technique is meant for. Okay, this will not give you a wrong result, but it will not give you the simplified version that you're looking for. Why is that? Can anybody tell me that? Somebody speak up.
Sir, if we take them together, then there will be less number of variables in one expression.
Exactly. So the point is, the whole idea behind the Karnaugh map technique is try to get as many cells together as possible. Cells of ones, of course, together as possible. Remembering, you are allowed to have singles, of course. You are allowed to have doubles, which are next to each other. You are allowed to have quads, which is either a rectangle of 4 or a square of 2, or 2 by 2 square. But the point is, they have to be next to each other. Or you can have 8 next to each other. Here you can't have 8. This simply doesn't have 8 allowed. But let me just see what you can really have. So first of all, the one important rule is you're allowed to repeat cells. Nobody is going to prevent you from doing that. Which means you don't have to take this alone. You can always take this. Okay? Now, these two you don't have to take alone. Since you're allowed to repeat cells and you want to take as big as you want, this is what you look at. Okay? The final one, there are 2 left. Well, actually, you don't have to take them separately. What you have to do is just take these 2 together. Remember the wraparound. There is the only tricky bit here. That is, these 2 are really next to each other, although it may not look like they are next to each other because you are allowed to wrap the whole thing around. That's the only thing that you need to worry about. Of course, you might argue that you could also have taken this, which also would have worked, except that now that you've already taken this, there's no point in taking that again. Once you have already taken all the ones, you don't want to complicate things by adding more. So what does the expression really look like? It looks like AC for this. These 4, again, cells of 4 means 2 letters. These 4 would be in C, in D. So that's CD. These 3 letters is in A, in B, in D. So this is ABD. And these 2, again 2 letters. Is all. If you are ever confused, just think of what it can't be. Can it be A? No, it can't, because one of the things is inside A, one of them is outside A. So A doesn't count. So there's no A here. Both are outside B, so this is B bar. Both are outside C, so C bar. Both of these are outside D, so D bar. So that's what the simplified version for this function is. Okay. So what the Karnaugh map allows you to do is try to make you look at the thing and try to identify these patterns. And since you're allowed to repeat cells, as long you're allowed to repeat cells, but you don't really want to overdo it. Like you can repeat this and this again. But since you've already taken into account this, you will not want to repeat this again. You're already done with it. If you took this also, you would add one more term to this expression, which will be, if you took this one and this one, the other term would be plus a b bar, c bar. No, not c bar. One is in C, and one is outside C. So no C involved, b bar. This will be correct. The expression is still correct, except that you have added one extra term which was not needed. Even without this term, the expression was already done. Okay. So the rule is identify bigger structures, the bigger the better. And remember, the structures have to be quads, either singlets, doubles, quads, or rectangles of 8 octets. And this wraparound is the only tricky bit. Other than that, everything else is easy. Now, if you were to try to write this down in terms of the Boolean functions individually and try to simplify this, let me guarantee you the simplification process will be rather complicated. This is way, way easier. You just take a look and it's done. Just to illustrate that in some detail, let me just, or before you go there, how would you know which cells to fill up? For this, there's a simple rule, which is treat the ABCD inputs here to each cell as if they were making up a full binary number. So, for example, these cells are all inside A. So the A letter, the first one, is 1 for each one of them. For these columns, A, the first one is always 0. For this, the second one, which I have written in blue, is always 1. For the ones outside these two columns, B is always 0, right? So if you follow this, you will be able to assign 4 numbers, zeros or ones, to each cell, which essentially will make up a binary number with 4 bits. And if you just read off the binary numbers in easy to read decimal version, this is going to be 0, this is going to be 0, right? 4 zeros. This cell is 1. The only tricky thing to remember is this is not 2, this is actually 3. 0, 0, 1, 1. 3 is up here. 2 is up here. So this goes 0, 1, 2, 3. Now what's the difference between this and this? Well, here the B, the second bit, was all low. Here is everything else is the same, just the second bit has gone high, which means you have added 4 to the decimal number. So instead of 0, 1, 3, 2, this is 4, 5, 7, 6. 4 more than these. The only other tricky thing, again, which is the same thing really, just like 0, 1, 3, 2. So after 0, 1 comes this one. Here, after these 2 columns comes this one. So that's why 8, 9, 11, 10. And this is the last column actually, always written in the middle, is 12, 13, 14, 15. So once you get the hang of it, it's pretty easy to remember that just one thing you have to remember, the 0, 1, 3, 2, the 3, 2 switch. Everything else follows automatically. So each of these can be easily identified by a single decimal number. Or if you are really into the game, you would not really be using decimal numbers for this. You will be using hex numbers. I hope everybody knows what hex numbers are. And you must have seen plenty of hex numbers anytime you have gone onto the internet and looked at any IP address. The hex numbers are, of course, base 16 numbers. Okay, numbers written to the base 16. Okay, and not base 10. And there, of course, what you will do is write 0, 1 up to 9, and then you will follow them up by A, B, C, D, E, F. So these A, B, C, D, E, F stands for what we call 10, 11, 12, 13, 14, 15, 16. So if you have seen things like FF dot EC dot 01 in an address somewhere, or a network mask or anything, if you have dappered with the internet, you will see things like this. Or the MAC ID of your phone. These are actually numbers in the hexadecimal system. The reason why you use hexadecimal system is very easy to, because 16 being a power of 2, it's very easy to convert between hex and binary. Well, there are other reasons, but that roughly is one of the ways of identifying these cells. But for the timing, we will just call them 0 to 15. That's the 16 decimal number starting at 0, ending at 15. The ordering has to be remembered, but it's really rather easy to remember once you remember the 0, 1, 2, 3, this switch between 2 and 3. How is that useful? Well, for that, let me just finish with the 7-segment display thing that we talked about. And yeah, any questions? Yeah.
Sir, is there a particular reason for the choice of ABCD cells? I mean,
No.
the ones you have chosen
No.
for A, B, C, and D.
There are no reasons. That's just conventional. You could switch them around, except that this is the A goes to the top column is sort of, you pick A first. Okay, you could have taken the first 2 rows, of course. Doesn't really matter. But point is, no matter which way you do it, this you might be wondering whether I can make this look like 0, 1, 2, 3 by choosing things differently. You simply can't. That is something you can figure out yourself. This switch of order will always happen, no matter which way you put your A, B, C, and D. It's best to stick to one convention because this is the standard one. You start with the first 2 columns being A. Of course, if these 2 are A, then these 2 cannot be anything else, has to be A bar. So B has to be something which has an overlap with A, because of course you will have to allow for the possibility that some functions are there with both A and B are high at the same time. So A and B will have overlaps, and there will be some columns which will not overlap. So you'll have to take these 2. Of course, you could label this as C as well. Doesn't really matter, but this is standard, the one we have used. The one thing which you cannot do is you cannot rearrange your ABCD in other ways and get a neat 0, 1, 2, 3, 4, 5, 6, 7 labeling for these cells, if that is what you're looking for. You can't do that. Okay? But you're right, this is conventional. There's no absolute reason why you have to follow this, except that if you break the convention, then other people will have a lot of difficulty in following what you're doing. Coming back to this was the example we talked about, the 7-segment display. Okay? For the timing, kindly ignore the leftmost column where the hex numbers 0 to F have been labeled. What I've done is I've put in these 16 input combinations and labeled them with the decimal numbers as well, just because that's what we are, both because it's going to be useful for figuring out our function, because what we want to do is display these decimal numbers, at least the first 10 of them, not really the last 6, because these are not digits, but these 10 are digits, and we want to display them in my 7-segment display. Okay? So if you have remember what this is going to be like, these are 0, this is 0, this is 1, this is 2, 3, 4, and so on. Just reading the binary number in decimal, that's it. And when you have that, it will tell you whether this segment will light up or not, whether this segment will light up or not, and so on. What I've done is I've provided the entire table for the entire 7-segment display, but you can easily figure it out. For example, let's look at this column, F, for example. F is this bar. When is this high? For the number 0, of course, 0 is written like this, right? For 0, this is high. For 1, which is this, for 1, this is low. For 2, this is again high. So 1, 0, 1. For 3, again high, that's why 1. For 4, which looks like this bit does not light up. This LED or whatever it is will not light up. So that's again low, and so on. So this is how you build up the table. The important thing is, once you've gotten here, Everything below this are don't cares, because if you're doing a 7-segment display which will display by decimal bits, you're only worried about 0 to 9. You don't care what the output will be when the input looks like it's a number 10 or 11. That input should never come to your circuit anyway. Okay. So what you do, you fill up the Karnaugh map. How do you fill up the Karnaugh map? Let me just blow this up a bit. You fill up the Karnaugh map just by using the rule. This is 0, this is 1, this is 2, this is 3, and so on, and just put in the ones and zeros in. In fact, in this case, here we are filling up the Karnaugh map for the function small a, that is something which tells us whether this one lights up or not. And for small a, what you need to do is take a look at, well, the easy way to do it is identify that there are very few zeros, right? 0 is only for 1. That is, a will not light up. This one will not light up only when there's 1 as your input, or when there's 4 in the input. For 4, this will not light up. Everywhere else it lights up. So what you do is, instead of filling up the ones, you fill up the zeros. You fill up the 2 zeros at cells marked 1 and 4. Fill up ones in the other cells marked 0 to 9. And then put crosses on the other 6 pieces. Because the crosses just show that it don't care whether it's zeros or ones. Okay? Now this is where the important thing comes in. This is again one of the reasons why Karnaugh map is so important. The don't cares can be anything, but you could use a don't cares to simplify your expression a lot, because they can be anything. You will just use them to whatever simplifies your expression. Now that is very difficult to judge if you were just using Boolean algebra and just using the standard laws of Boolean algebra and trying to do it algebraically. Graphically is very easy. Just take a look. First thing you would do is realize that you have 4 ones here, but why have only 4 ones next to each other if you can have 8? So all you do is to simplify these 4 ones, you just don't block them together. You make these don't cares also ones. Remember, don't cares can be anything you want. Anything you want, but for a given function, of course, if you have chosen these cells to be ones, they have to stay on being ones. So this is, you make them ones, you take them all together. That's it. Okay. So that gives you C. So one term in the expression, just C. Okay. Now look at these 2. You will of course not take them together. You will take all 4 of them together. But why take only 4 of them together? Why can't we take all 8? Because these are don't cares, right? So we will just make them ones. So we've got 8 next to each other. So that's A. So the advantage is this one tells you that the don't cares should all be 1, because that's what simplifies the thing the most. Well, not only that, now that you have already put these as ones, you can't go back. They have to be ones. But fine, you have this single corner sticking out. Just put all of the 4 together. Repeat, doesn't matter. Only 4, because remember, you can't make 8 out of it. There's a 0 here which prevents you from getting 8. There's a 0 here which prevents you from getting 8. You may get 9 contiguous ones in a square, but that doesn't count. It has to be 0, 2, 1, 2, 4, or 8. So this one and the corner ones. This is the trickiest one to get, because corner ones, you have to remember all the corners are wrapped together. So this single one in the corner is actually all 4 together. So that's C plus A plus BD plus B bar D bar, and that's it. That's the simplest version for A. Is that clear to everybody? Any questions? Well, just to sort of contrast this, when say decided that all the don't cares will be zeros, that's arbitrary. They don't cares. Why give them ones? But then you will only get this square, this one, this dyad, and this dyad. And this is the expression you will end up with. This, of course, is the correct expression, the most simple possible expression for this function. But you don't really want this function. All you want is these green zeros, they could be ones or zeros, I didn't care, right? So by using the don't cares, I can make it much simpler just by looking at, by in this case making them all ones. By the way, in this case, it's not always the case that making the don't cares ones help. But what helps, that's something you can easily see by looking at the Karnaugh map picture, trying to put as many together as you can. Just to point out here, I have all the other letters B, C, D, E, F, G. They have all been drawn in the Karnaugh map cycle. Let me just show you one example. Let's say this one. This is for the letter E. Why is this the one for the letter E? I think you should be able to do it yourself now. If you think you've understood what I have said so far, you should be able to do it. Now, how would I go about simplifying this? If I did not worry about the don't cares, I would see that there are two ones together. These are together. Two ones here. That's it. So these are two ones together. These are two ones together. But can I simplify things any further? So if I just look at these two ones together, this will be B bar. Okay, so what will these be? If I did not worry about the don't cares right now, just try to write them down. I will get B bar, C bar, D bar. For these two ones, I will get A bar. They're both outside A, right? A bar, and then B will not feature, but it will be C, D bar. Is everybody clear about that? But you should also be clear that this is not the best thing to do. The best thing to do would be to have these two ones, but try to make it as big as possible. So why don't you just do this? Take all four together as ones. Don't cares, remember, you can make them anything. So that will of course be much simpler, right? You will, if you do that, what you will end up with is the correct expression in this case will be, or the simpler expression. This is also correct, but the simpler expression will be C, D bar. In C, outside D. C, D bar, of course, you would agree that it's much simpler than any of these two expressions. But that's not all, right? You have these two to begin with, to end up with. So how would you simplify that? Any idea how you would change that?
So it is B bar, D bar.
Yeah. Basically, what you do is look at these two, not only these two together, but also look at these two together. Right? Because all four together, right? They're all together. So that's outside B, outside D. And this actually tells you two things at once. First of all, it tells you that the simplest possible function that will implement E is not this, but this. And it also tells you which ones to choose as, which one of the don't cares do you want to choose as ones. You want this one as one, this one as one, but all these you want to keep as zeros. Do you get that? You don't really want to make those ones. It's not true that you want to make all the don't cares ones and that's going to help. Okay? This is critically important.
Excuse me, sir.
Yeah, go ahead.
I think I've missed it, but if the second row of A, the row of A that coincides with B, if we make all of that one, what would go wrong there?
No, it will not go wrong, except that it will. Do you really need that? You already have done it with two terms, right? If you made these all ones, then you will have to take those also into account.
Yes, sir.
You are right in the sense that you could make them all ones, but you did that and you will get a simple expression. You will get AB, right? Not too difficult.
Yes,
but that's an additional term, right? You already had two terms which are doing the job for you. If you made these ones, you would have to add an AB to the whole expression. It's not a question of whether that term is simple. The question is, do you need it? You already have the answer. Why make it more difficult for yourself by adding one more term?
Yes, sir.
That's the point. The point is, if you have already gotten all your ones, in place, the ones which have to be ones, not the don't cares, but the ones which have to be ones, you have taken all of them into account already, then you have done it, right? Then you don't need to put extra stress on the system by adding more terms. Is that clear?
Yes, sir. Thank you, sir.
So these ones would be correct, would actually implement the same function as far, not the same function, but the same function as far as 0 to 9 inputs are concerned. But why make life difficult? Here, on the other hand, you have these two ones, right? If you wanted to simplify this, you would definitely make all of these ones. Why? Because that will give you a octet. The don't cares can be chosen any way you want. Since you already have two ones here, you would make an octet out of this. Because that will, remember, try to go as large as possible. So quad is better than a doublet, an octet is better than a quad. So that's basically it. And I have one final example here, which is just some arbitrary function I've thrown in. So just to sort of quickly illustrate what I want to do here is just the idea. This is our x here, but it's crying out. Since you can make this 1 or 0 or whatever, you will make this a 1 so that you get this. Could also make all of these ones and add this term, but this one has already been taken into account, right? So adding this, making these ones and adding this one extra square will give a simple term, at least simpler than otherwise, but you don't need the term at all. On the other hand, this one you take with this, okay? This one you take with this. That still leaves out this one, so that you take with this one. So 1, 2, 3, and 4 terms in the final answer, and only one of these need to be non-zero. You could of course say I can make this a 1, I can take doublets like this. You can't do that. That will also work. That will be just as simple or as difficult. That's equally correct, but not necessarily what you need to do. What you will not do is take this doublet, also make this one, and take this doublet. That's stupid because you have already taken care of the one. Why do you want to add an extra term there? Okay, I'm done. Thanks for being here. We'll meet on Friday, and we will wrap up the course with discussions on Friday. But there will be quite a lot of videos in between on digital circuits. Of course, Wednesday is an exam. Just remember that. Class test, that is.